Good. Okay, yeah, thank you so much for inviting me. I'm a little sad I couldn't use the opportunity to actually visit Tübingen again, but yeah, hopefully it will come up at some other time. And yeah, I've tried to participate in some things. I couldn't do as much as I wanted to because I have a sick 4-year-old at home, but I've attended some sessions, also a breakout room right now, and I really enjoyed it. I think the talks were all of really, really great quality, and yeah, it was really fun. So yeah, today I want to talk about a computational explanation for domain specificity in the human brain. And what do I mean by domain specificity? Well, the last quarter century of cognitive neuroscience has revealed numerous cortical regions in humans with distinct and often highly specialized functions. So from recognizing faces to understanding language to even thinking about what other people are thinking. But it remains unclear why the cortex exhibits this high degree of functional specialization in the first place. Or, you know, more generally, there we go, why is the human brain functionally organized the way it is? And today I'd like to consider one of the best established cases of functional specialization in the brain, namely the visual recognition of faces. And actually first evidence for functional specialization of faces goes back quite some time to the early beginnings of fMRI, where you know, labs started to find that if you show subjects in the scanner images of faces and images of objects, some areas in the ventral pathway respond selectively to faces compared to any other visual category, and some, you know, respond to more to intact objects than to anything else. And these areas are not just activated when perceiving faces, but when you disrupt them, they produce a selective impairment of face perception. And that has been shown in patient studies that have lesions in face specialized areas, and they can no longer recognize faces, but their object perception is pretty much intact. And the other way around has also been found. And there's also evidence from TMS studies where you zap, you know, certain local areas of your brain, and you can see a selective impairment in object or face processing. So it seems like there's evidence for functional segregation of face and object processing in the human visual system. And just as a note that today I won't address spatial segregation of functions, so why certain things are at particular locations in the brain, but the more general phenomenon of any functional segregation in which certain populations of units are more critical for one task than another. Okay. And so for this functional segregation in particular, it remains unknown and indeed largely unasked why the brain exhibits this high degree of functional specialization. So is it an accident of evolution? You know, maybe it's just easier to add more modules once we learned more tasks to do, easier for the brain to organize this way than to redesign the entire system, or maybe there are computational reasons for why faces and objects need their own functional machinery. There's lots of hypotheses for why this could be. And another follow-up question is, you know, how does functional specialization arise? How does it develop? And what is needed? What do we need to build in the system for functional specialization for faces to emerge? So do we need any task-specific inductive bias? Is this something innate? Or is experience alone sufficient for this functional specialization to emerge? And today, I want to test a particular hypothesis, which is the hypothesis that the functional segregation of faces in the human ventral pathway reflects a computational optimization for the task of face recognition. And the idea that there might be computational reasons underlying the functional organization in the visual system is not new. In fact, I'm just mentioning a few works and papers here that go back to David Marr in 1982, but also Rickel and Jacobs, who all sort of had this idea of, by understanding the computational structure of the task, we might understand why the brain is organized the way it is, or why the visual system is organized the way it is. But at that time, there was basically no mean or no model to test this hypothesis, because we had no model that was anywhere near human level accuracy or performance in visual object recognition. And you might know where this is going. So this suddenly changed with the rise of convolutional networks, or CNNs, in computer science. And we've heard some really nice introductions about this morning. So I'm trying to keep this short, but basically in 2012, Krzyzewski et al. Developed AlexNet, a CNN optimized to classify images into object categories. And critically, these CNNs are image computable, meaning that they can be trained on natural images, like the image of the orange here. And this image then gets put through a cascade of operations, extracting features of the image, pulling those together, and eventually classifying the object category, such as the label orange here. In this particular architecture, AlexNet won the most important computer vision challenge at that time, and each following year, another CNN won the challenge, until by 2015, CNNs achieved human-level accuracy in object categorization. And despite still being far from human-level visual recognition in many aspects, and we've also seen examples for that this morning in Fabian's talk, CNNs are very useful and a big advance, not just for computer vision, but also for human cognitive neuroscience. Because these computational models are inspired by the brain's visual processing hierarchy. And in the last few years, several dozens of papers have been published showing that there's a high similarity between the features extracted at the different layers of a CNN and the different processing stages in the human visual system. And this is exciting because for the first time, we have image computable models of how human visual recognition might work in the brain. So how could we use those models to better understand human visual processing, or how can they contribute to understanding at all? And I actually, already had this slide, but this discussion came up this morning as well, because often when you talk about CNNs or artificial neural networks in general and the brain, the term black box comes up, right? Like, how can it be helpful to replace one black box with the other? How can that contribute to understanding? And in particular, if you come from a human cognitive neuroscience perspective, I think you can see the power in these models and everything that you can do and that you have control over that we can hardly do with the brain, and in particular with the human brain. So for example, we have full control over development. So we have full control of the learning stage. We can look at networks randomly initialized, fully trained, somewhere in between. We can vary the architecture, and by that, vary with what they start with, basically. We have full control over the training diet, so we can manipulate experience. We can, for example, easily phase deprive a network that is really hard to do in humans, if not, ethically just not correct. And train a network, and we know exactly what it's seen and what not. Further, all the analysis and experiments we do are data-driven. So we have large-scale data sets. We can run large-scale experiments that go way beyond any experiments that we can do with humans, given the limited amount of time we can do an experiment and their attention lasts and so on. And lastly, we have full access to representations. So we can read out representations on a single unit level, on a population level. We can even lesion certain aspects in the network and find out whether they're causally involved in a particular task and so on. So I would like to argue today that there are no black boxes, but in fact that there can be really helpful to test our hypothesis that we have from cognitive neuroscience about the brain, and test those in those models. And by comparing the models with the brain, we can also go back and say, okay, what do we have to improve in the models? What can we change to make them more similar or to make them more robust, for example. All right. So to go back to the research question that we had, so why could face and object processing be segregated in the human visual system? I want to present you a project today. There was a collaboration with Julio Martinez and Nancy Kenwisher at MIT and Alex Kell at Columbia University. And in particular, the first question we had was, okay, if there are any computational reasons for why these things like face and object processing might be segregated, could we use those models somehow to test whether face and object tasks require distinct representations? So can we replicate this double dissociation that we see in patients and in human perception in systems trained independently on face and object tasks? Or would the features that you get from a system that you optimize on one task, would it be also useful for the other task, and therefore supporting other potential accounts for why functional segregation. And then as a next question, what happens if you train a network on faces and objects simultaneously? Would you see, would that network be able to find, some sort of representation to do both tasks? Or would you actually see the same functional organization arise in CNNs without any task-specific inductive bias? So these were the main questions. We'll start with, do phase and object tasks require distinct representations? So what we did to test this question was we took a VGG16 architecture, which is a very common architecture, and also that has often been compared to the human and monkey visual system as well. And we used a randomly initialized architecture and then optimized and trained it to discriminate around 1,700 face identities that we took from the VGG phase 2 dataset. So that network was trained and optimized to discriminate identities, but hasn't seen anything else. So it's sort of the, this most specialized face module you can think of. And then we used the same architecture and trained and optimized this to categorize different object categories. So we took manually selected 423 prototypical object categories from the ImageNet dataset and trained and optimized this model to categorize those objects. And importantly, the number of images between those two data sets were matched. So both of the systems had the same amount of training, the same amount of experience, if you want. Okay, so now we have these two, two systems, one trained to discriminate faces, one trained to categorize objects. How could we now find out whether they're useful for the other task? So what we did is we had 100 held out identities. So these were identities that the network had never seen before, had never been trained on, 10 images each, so 1,000 images in total. We basically show those images to the network, extract the features from the penultimate layer, so we get these activation patterns for every single image, and extract those patterns for all the face images. And then we also had 100 held out object categories that we took from the things database. And these, again, were novel object categories that the network had never been trained or seen before, novel images. And we extracted the activation to those. And then we also did the inverse. So we showed the face images to the object CNN, extracted the activations, and the object images to the face CNN. So we now also get activations to object images from the face CNN and the inverse. Okay. So now to find out how useful those features are to do the task, what we did is basically just a linear readout. So in our case, we used a support vector machine to see how well can we decode these 100 different face identities, 100 way classifier. So this is on the y-axis here, the decoding accuracy using the features from the face CNN or the features from the object CNN. So that's what we found for the face CNN. So overall, features from the face CNN were really very useful to discriminate different face identities, despite them being novel identities. So the features even generalized within the same domain to novel identities. And that performance was almost at ceiling. When we did the same now from the features extracted from the object CNN, we found that performance was much worse. So the object CNN being trained on very generic object categorization, those features did not seem to work well to discriminate different face identities. And they were above chance though, so chance percent was 1%. So you can't say it didn't work at all, but definitely much worse than the features from the face CNN. And when we now did the opposite for object decoding, we found the exact opposite. So now the features from the object CNN were more useful to categorize objects than the features from the face CNN. So it seems the object trained network does not do well on the face task and vice versa, suggesting that the representations learned for one task do actually not readily transfer to the other. And each task appears to benefit from specialized task-specific representations. And that already sort of gives us an potential explanation for why face and object task might be segregated in the brain. So do face and object tasks require distinct representations? We find yes, the representations are actually suboptimal for the other tasks, giving us a first sense why, from a computational point of view, it might make sense to segregate those two tasks. Okay, then we wanted to go a step further and ask, okay, what happens if we train a network on both of these tasks simultaneously? Would this network be able to learn these two tasks the same way as the single trained networks? And would we see the same functional organization arising in those networks? So what we did to find out is we took the same VDG16 architecture, randomly initialized and trained it from scratch. But now this network, we trained it on faces and objects by basically concatenating the face classes and the object classes into one large classification layer, and then training and optimizing this network on mixed batches of faces and objects using both data sets. And what is important here is that while we know that some of those classes are face classes and some of those classes are object classes, for the system, this was just one large task. All of the classes, it was just one task, one classification task, where all the classes were in one large task. So it didn't know anything about faces and objects, or they have any different meanings to other anything. So no task-specific inductive bias for faces in this model. And so the first question we had was, okay, can the system actually learn both tasks? And in particular, would it perform both tasks well? Would it perform it as well as the singly trained networks? Because if you think of like, okay, if there are really specialized representations that each of those tasks use, and now you take the same system and train it on both tasks, you could well imagine that the performance would actually go down because it didn't have enough capacity to do both tasks. Okay, so that's the first thing we wanted to find out. So what we did to test is we looked at the test performance. So when you train a network on visual categorization, you always have some left out images that you compute your accuracy on. So for the face CNN, that's the performance on the face task. For the object CNN, that's the performance on the object task. And now the critical question is, how well would the dual task network perform, and would it perform worse than any of those singly trained systems? And that's what we found. So it was basically able to perform both tasks as well, nearly as well as the singly trained models. So face and object tasks can be performed well in one system, which was a bit surprising to us, so far with our hypothesis. So it sort of, could mean, okay, this network maybe now discovered some shared feature space. And so, there's no computational reason to actually segregate those two tasks. However, there's an alternative explanation, which is, what if this network spontaneously discovered task segregation and basically in the hidden layers of the network sort of assigned some of the units to do the face task and some of the units to do the object task, and sort of had like two subsystems in one system. And that's what we wanted to find out. And what we did to test this is we performed lesion experiments in the dual task network. And so that's another thing you can do in those systems, which is basically doing neurophysiology in an artificial system, which is just really great that you have that tool to understand what's going on in the model. So our idea was, the method we used was that we said, okay, let's drop each filter in every convolutional layer in the model, and let's show it batches of face images, many face images, and then compute the loss on the face classes. So all the classes that belong to the images in those batches of face images. And the idea being that if a filter is important for the face task, you should see an increased loss when you drop it. Whereas if it's not important for the task, the loss should not be affected or maybe even go down. Okay. So we did this for every convolutional layer, and I'm just showing you the fourth convolutional layer here. So what we see is, what you see here is the filters and then the associated loss when dropping that particular filter, and while showing it batches of face images. And then we rank those filters according to their associated loss on each task. So you basically get the ranked filters, and in the top 20% or something here are those filters that you assign to be as most important for the face task. However, we then tested the task specificity of this ranking by lesioning the top 20% filters altogether that most affected the performance, while measuring performance on an independent validation set for the face and the object task. So what we wanted to know is like, okay, it's important for the face task, but is it selectively important for the face task? Or would it also impair the object task if we lesion those filters? And then just for completeness, we did the same thing, showing batches of object images. So these are the same filters, but now ranked by how important they were for the object task. And we would again lesion the top 20% of those filters to see which task they would affect. Okay, so does functional specialization spontaneously emerge in the system? We started by looking at the last convolutional layer. And the idea was if there's any segregation in the system, then we should see it. We should definitely see it towards the end of the system. So we started with the last convolutional layer, and we dropped the top 20% face filters. We lesioned them all together, and then now look at the performance of the independent validation set on the face task and the object task. And on the y-axis here is the normalized test performance. So 100 is what the original performance was. Baseline, basically. Okay, so that's what we found. So lesioning the 20% highest ranking face filters strongly impaired the performance on the face task, but only minimally impaired the performance on the object task. And we then found the exact opposite when we lesioned the object filters. So now we were much more impairing the object task than the face task. So these findings demonstrated double dissociation in the network, where face and object task rely on distinct features in the last convolutional layer. So the network basically spontaneously segregated itself into distinct subsystems for face and object recognition, despite the lack of any task-specific inductive bias that might have encouraged this outcome. So there's evidence for functional specialization in one system, great. And then we went one step further and asked, okay, at which processing stage does this domain specificity arise? Because we know from human visual processing that the early visual processing stages between different visual categories are shared, and then only in some mid-level or later stages of processing is when tasks become specific and we see more specialized areas coming up. So what we did is we basically performed the same analysis that I just showed you in every single layer of the network. And then we computed a segregation index, which is basically just the combined selectivity of lesioning the face or the object units. So how selectively we're lesioning the face units, was lesioning the face units only impairing the face and not the object task, and vice versa for the objects. And that segregation index is bounded between -1 and 1, where 1 indicates the maximum segregation that you can achieve. So now let's look at this combined segregation index over the layers of the network. And that's what we found. So basically in the early layers, there was almost no segregation between the two tasks. In some mid-level stages is when the tasks started, the units started to become segregated, and it became highly segregated at later stages, much as we see in the primate brain. Okay. Yeah, this another similarity basically here that we found that we thought was exciting. And then there's one more thing that you can do, and it might not teach you a lot, but it's still very interesting to do so, which is you can actually ask what features are those face or those object filters actually extracting. So what you can do is you can visualize the preferred stimulus for each filter in your network by presenting the network with some random noise and then modifying this input to maximize the activation of filters that ranked high on the face or high on the object task. And that's what we did. So I'm just showing you two example filters that were ranked really high on the object or the face task from layer conf9, so some mid-level processing layer here. And what you see is that these the object filters were pretty generic features and shapes that they responded to, whereas for the face filters, they sort of started to resemble face parts. So you could maybe see a nose in here, and that sort of looked like an eye, and we saw many more of those features. And then when you do the same thing in the last convolutional layer, the first thing you see is that the receptive field sizes increase, which is basically a result from the implementation of the architecture. But also what you see is that while you get more complex generic shapes for the object filters, you actually see more or less holistic faces for the face filters, where there's eyes and the nose and the mouth, and they're really like in the appropriate configuration and everything. All right, so segregation of face and object processing spontaneously emerged after some mid-level processing stages, like in the human visual system. So can the same functional organization arise in CNNs trained on faces and objects without task-specific inductive bias? We find that yes, functional specialization spontaneously arises in a dual task network without any task-specific inductive bias for faces or for those two tasks. So again, while this dual task network now shows us, like, really resembles the functional segregation we see in the visual system, what we wanted to know is, are the learned feature spaces to perform both tasks actually similar to the human visual system? So did it learn the same solution, or did it sort of come up with a different solution for those two tasks? And to measure that, what we did is we measured human perceptual face representations. So we asked human subjects to perform a multi-arrangement task in which they see many different face images on the screen, and they have to arrange them in a circle according to their perceived similarity, and they do many of those trials. And as a result of that, you get a representation of the similarity matrix that we've also heard before today, where every value every value in that matrix indicates the perceived similarity between a pair of images. And now you can do the same thing with your models by showing it the exact same images that you show your human subjects, extract the features, and then compute the distance by, for example, using 1 minus Pearson correlation, and put those in the matrix, right? And with the representational similarity analysis, what we didn't do in representational similarity analysis is then correlating those two RDMs to see how similar are the features represented in human perception versus the features represented by your models. So are the learned representational spaces similar to human perception behavior? We started by looking at the face-trained CNN. So what you see here on the y-axis is the correlation between the deep-net features of representational spaces and human behavior for every single layer in the network. And what we see is that correlation constantly increased for the face CNN, and even reached the noise ceiling. So that's the maximum correlation you can achieve given the variability across subjects in the late layers of that network. And when we did the same thing for the with the features from the object CNN, that did not correlate as well, and actually never reached the noise ceiling. And then we also looked at the representation from our dual task network. And that was very interesting, because what you can see is that it matched the object trained network in the early layers, because it sort of has these more generic features, less specialized than a face trained model, but then it also has the face specialized features here to achieve that high correlation in the late layers of the network. And then we actually did the same task, not using face but object images, comparing that to human behavior, and here we found the exact opposite. So now the object CNN and the dual task network correlated well with human behavior, while the face network did not. So the dual task network actually captures human behavior in both face and object tasks, and thereby overall outperforms any of the single trained networks. All right. So to summarize the results I've shown you today, I've shown you that face and object tasks require distinct representations. So one representation does not automatically transfer to the other task. I've also shown you that one system can actually learn both tasks. And when we started to look at how did it solve this, what we found is that functional segregation emerged without any task-specific inductive bias in this network by basically assigning some of the units to do the face task and some of the units to do the object task. And then lastly, I've also showed you that the learned representations resemble those in humans. And yeah, to get back to the particular question about functional segregation of face and object processing that are raised at the beginning, what these results suggest is that for why face and objects might be segregated in a visual system is that function specialization for faces may actually reflect a computational optimization for the task. And they further also suggest how this may emerge by basically saying that at least in these models, visual experience alone was sufficient for functional segregation to emerge. We didn't need any task-specific, face-specific inductive bias or template or anything. And yeah, to go back to the really big picture, I think perhaps the most exciting aspect of this work is the fact that we can move beyond simply describing the organization of the brain by saying, oh, let's see what this part does and let's see what this part does, but to asking normative questions about why the brain is organized the way it is. And using those methods, we can actually ask a suite of further why questions, such as which visual categories require segregation and why these? What functional segregations are expected for domains other than visual classification? And should we expect to find functional segregation, for example, for syntax or semantics in language processing based on the computational structure of these tasks? So yeah, I think network optimization and dissection provide powerful methods to tackle questions about why the brain is organized the way it is. And I think that's a really exciting new pathway. And I'm really curious to see where this will lead us. And with that, I'd like to thank you for your attention. Thank all my collaborators and funders. And yeah, this is the link to the preprint if you want to read more about this work. And yeah, always feel free to reach out if you have any questions, and I'm looking forward to the discussion.
Thank you very much.